Okay, so I thought it would be a good idea to go through some of the solutions to the day one classwork we had when we first started logistic regression. It's been a while since we've looked at this, so I just wanted to go over a few things. So the first couple questions I think are probably not an issue for anybody, but if you have any questions about any of that, do let me know. The basic thing that we can see in number 2 by doing a scatter plot, side-by-side box plot, and looking at a few summary statistics is just that the temperatures tended to be lower for the launches that had some evidence of O-ring failure, and the temperatures tended to be higher for launches that did not have any evidence of O-ring damage. Just FYI, at the top of page 2 here, you can see that I created a variable called launch that I added to my shuttle data set. That was not necessary for you to do to be able to answer the question or do what I'm doing here to make the little table. I just wanted to show failure and success, but it really doesn't matter. You could have done it with the zeros and the ones. Okay, so what we're interested in estimating is the probability of a successful launch, one that has no evidence of O-ring damage, based on the temperature. So doing what we know how to do is creating a scatter plot and a linear model of success versus temperature and coming up with a regression line based on that, which you can see down here. I got the coefficients from the model summary just above. So the estimated probability of success is negative 1.9 plus 0.04 times the temperature. Now when we look at a scatter plot with the regression line on it, we can see that it doesn't seem like the right kind of thing to do. And one of the reasons for that, we can see that the line goes above a y value of 1 and below a y value of 0, and so that means that it's going to give estimated probabilities bigger than 1 and less than 0, which don't make sense. So we'll come back to that in a minute. I gave you a couple of ways to make predictions based on the model, putting in a value for temperature and coming up with the estimated probability. So when the temperature is 60 degrees Fahrenheit, probability of a successful launch is estimated to be about 0.34. When the temperature is 85 degrees Celsius, the probability of a successful launch is 1.3. So there's one of the probabilities that doesn't make sense, right? There's no such thing as a probability bigger than 1. So in that case, our model is not doing a good job. So in number 4, that, of course, is the main reason why the least squares regression line is not a great model for predicting this probability. And in addition to the probability bigger than 1 that the model gives when temperature is 85 degrees, if you look at a temperature of 31 degrees, which was the temperature on the day that the Challenger had its disaster, the model predicts a negative probability, 0.75, which again doesn't make any sense. There's no such thing as a negative probability. So in this situation, when we have a binary categorical response variable, what we want to do is fit a logistic regression model. And one of the reasons we use logistic regression is because it always returns values between 0 and 1. Now the thing is that in order to create that model, we have to apply a transformation that we haven't used before, and it's a little bit more complicated than the ones we've seen. Right? We've had logarithmic transformations, we've had square root transformations. This is called a log odds transformation, or also known as a logit or a logistic transformation. So before we can actually take the log, we're not taking the log of the response variable. We're looking at pi as a probability of success, and then based on that value of pi, computing the odds of success, and then based on those odds, finding the natural log of the odds, which again, a statistician just uses log and calls it log for natural log. So when we transform from probability of success pi to the log odds, as they're called, we say we're performing a logit or logistic transformation. Now, before we look at that any further, I wanted you to practice with calculating based on a probability finding odds, and based on odds finding probability, and you should become pretty fluent at going back and forth this way. So the first three parts in number 5, A, B, and C, give you probabilities and ask you to come up with odds. Now we do have the formula, pi over 1 minus pi, but there's a couple other ways you could think about this that might be a little bit easier. One way is to imagine a spinner, and suppose that I have this cut into 4 regions, and let's say that my probability of success is 1 out of 4. One way I can think about the odds is as the ratio of the success part to the non-success part. So in other words, in this case, if my pi value, my probability of success is 1/4, then the odds are 1 to 3. I have 1 part success to 3 parts failure or not success. So the odds would be 1 to 3 in that case. Another way you can think about odds is that if you are given the probability as a fraction, and that probability is, say, A over B, then the odds are computed as A over B minus A. So again, the B minus A, B being the whole, the B minus A is getting you the other parts that aren't the success part. Then for parts D, E, and F, I gave you odds and asked you to compute the probability. So one way is if you take that original odds equals pi over 1 minus pi and solve that for pi, which you might want to do on a separate sheet of paper, just a little algebra exercise, then you should find that pi is equal to the odds over 1 plus the odds. Another way you can think about it is if the odds are A to B or A over B, then the probability is A over A plus B. So that is, in fact, the part to the whole. So probability, if we're given odds, we can think of probability as the ratio of the part to the whole. So going back to the example that I wrote on the paper a minute ago, if we know that the odds are, say, 1 to 3, then that means there's 1 success part and 3 non-success parts for a total of 4. So the probability would be the 1 over the 1 plus 3, or 1 out of 4. So again, whatever way you have of visualizing this that works for you is totally fine. Just wanted to give you those as possibilities. Okay, so what we are doing now, we have this binary categorical response variable, and we want to use linear regression, but what we are fitting that linear equation to is not the success probability pi, it's not the zeros and ones, it is in fact the log odds. So we perform this transformation going from success probability pi to odds, pi over 1 minus pi, to log odds. And the log odds is what we fit that linear equation to. Now, there are 2 forms of the logistic model. One is the logit form that I just described, and the other is probability form that you can see here. And I asked you in number 6 to do the algebra to go from one to the other. So just for this one time, I'm going to write the log as the ln. But again, a statistician just uses log. So we start with this logit form, as it's called, where the log odds is equal to the linear equation beta naught plus beta 1 times x. Now we want to solve this for pi. The first thing we're going to do is exponentiate. So we raise e to both sides. And in doing that, the reason for that is on the left-hand side, when we raise e to a natural log, we just get the argument, or whatever's inside the natural log. Okay, so now we want to solve this for pi. I would probably sort of cross multiply, and I'm going to then distribute the e to the beta naught plus beta 1x through the 1 minus pi parentheses. Oops, that's going to be a minus. So again, you might put one extra step in between these last two that I just did. I multiply both sides by 1 minus pi, and then I immediately distributed the term on the right hand side through the 1 minus pi parentheses. Now I'm going to add back that term with the pi in it from the right side to the left side. And then I'm going to factor a pi out of the left-hand side. And then I'm going to finally divide to get pi by itself. And that gives me what we call the probability form. So I can either have the logit form where the log odds is equal to this linear equation, or I can backtrack that to come up with a probability that's equal to what's known as the logistic equation. All right, and then last but not least, I just wanted you to look at a few different values of beta naught and beta 1 and what effect they have on this logistic curve. And so basically what I put here in the solution is that the value of beta naught is what determines the horizontal position of that logistic curve. And in fact, the vertical midpoint where the pi value is 0.5 happens when x is negative beta naught over beta 1. And any of you that have a calculus background, you might think about how you could figure that out using calculus. And then the value of beta 1 controls not only the steepness of the curve, so the higher the magnitude of beta 1, the steeper the curve is, but also whether the curve is increasing or decreasing. So if beta 1 is positive, that logistic function is increasing, as in these first 6 pictures. When beta 1 is negative, then the curve is decreasing, as in this second group of 6. Okay, so again, if you kind of sort of look at this solution sentence a little bit and sort of look carefully at the graphs and how beta 0 is changing versus beta 1 changing, and just make sure that you understand the effect of the beta naught and the beta 1 on that logistic curve.